All right, so in this module, we're going to go over an example of a non-steady state diffusion problem. So again, this is going to be on our quiz. So you'll go over there after I give you these instructions and try the best of your ability answer this question, and then come back and we'll work this together after you've had a chance to look at it yourself. So I've reprinted the semi-infinite diffusion equation that we talked about in the previous module. And we're going to use that to study an example of what we call carburization. So basically, carburization is diffusing carbon into an atom. We talked about the case hardening of a steel, and that's an example of what we're doing here. So we start with an alloy that initially has a uniform carbon concentration of 0.25 weight percent, and we're going to treat this alloy at 950 degrees Celsius. And then if the concentration of the carbon at the surface is suddenly brought up to 1.2 weight percent and maintained there, we're asking how long will it take to achieve a carbon concentration of 0.80 weight percent at a depth or position of 0.5 millimeters below the surface. And so here I'm giving you the diffusion coefficient or diffusivity of carbon and iron at that temperature here. And again, we can assume that this steel piece is semi-infinite. So if you want to, I recommend drawing a diagram for this and then seeing if you can solve for the term asked for in the statement. And again, pause the video, try to do that, and then come back and we will discuss the results. So let's take a look at the example for non-steady state diffusion, talking about carburization. So if it's helpful, I always recommend making some type of sketch, right? So here's our infinitely long alloy bar, so steel alloy. In this case, we have the problem statement. Part of the goal here with this problem is it's written out as a word problem, and you need to equate the different values it gives you to the terms of the expression that we had, right? So reading through this, it says there's an example of carburization. It says the alloy initially has a uniform carbon concentration of, so the key there is initial and then concentration. And so that's our C naught, and that's 0.25 weight percent carbon. All right. And so that basically means initially in this bar, if the concentration axis is here, right, we have an initial concentration throughout this bar of C naught. Right. The temperature is 950 degrees Celsius, is the next part it says. And then it says the concentration of carbon at the surface. So surface, that should tell you CS in this case. So CS is equal to 1.20 weight percent carbon, right? So that tells us that at the surface here, it jumps up to this concentration here, CS. And then it's asking how long, so T, so we don't know what that is because that's what it's asking for. But it says to get to a position, or sorry, to get to a concentration of 0.8 weight percent. And so that's going to be our concentration at our position because it's saying that the position is 0.5 millimeters. And then it gives us the value of diffusion coefficient, which is D, for carbon in iron at that temperature of 1.6 times 10 to the minus 11, and this is meters squared per second. And it tells us that it's semi-infinite, so this problem up here, right? So we basically want to look at a certain position. So this is position here, X. So we want to look at a certain point, X, which is our 0.5, and we want our CX to be 0.8. So somewhere in the middle there, right? So this is CX, and this is X, right? So this is basically what the problem is looking at. And so if it's helpful to draw it, you might represent the concentrations and position in this type of plot of a bar, right? This is our steel bar, steel semi-infinite bar. So this is going to infinity over here, and then this is 0 over here. Okay, so let's look at the problem, right? This is the equation that we're going to be using, because this relates the concentrations that are given to us to the position and time and diffusivity, right? So the first question you have to ask yourself is, what are we going to start with, right? Because this is an error function, we're going to use the tabulated values. And so we either need to know what's inside the error function, or we need to go what's outside, which should be the left side. And so if we look over here and see what we have, well, we don't have time, right? So it automatically tells us we don't actually know what this whole term is. And so we do have, though, all of the concentrations. We have CS, CX, and C naught, right? So we can solve for all of this and get what this is. So if we rearrange this expression, we get the ERF of x minus 2 square root of dt equals, and then that's going to be 1 minus this term over here. So I basically flipped the expression, just rearranged it. So we have this. And for this, I'm just getting rid of this. I'm just calling this CX because that's the same thing as what's up here, right? So what this is going to tell us is that if we're thinking ahead to the tabulated values, we are going to know what the ERF of this term is. And so we're going to be able to plug in this number to the table, see what the value of this part of it is. So let's go ahead and do the actual calculation here, though. So we know what this is. So this is going to be 1 minus, and this is the concentration of X, so 0.8 minus 0.25 over 1.2, 1.2 minus 1.25. So we know what that is, and if we plug in all those numbers, we should get that this is 0.4210. So the ERF of this is equal to 0.4210. All right, so this is where the tabulated values come in. And so this is where we're going to have to look at that table. And so we'll go ahead and look at the table, and then we'll see what we can do with that. All right, so I've opened up the textbook, and I'm looking at table 6.1, so you can do that in your book as well. And I have the value, right? So I know the ERF of this expression is equal to 0.4210. So if I'm looking at the table up here, it says ERF of Z, right? So we can assume that this term here is Z. And so we know what the ERF of Z is. And so let's see if we can find one that matches with this. So we're going through, it's too small, too small, too small. And then eventually you see that it's pretty close to 0.4284. But we're a little smaller than that, right? So we could just assume that it's close enough and use the equivalent value for Z and assume that this is 0.4, right? Because this value corresponds to the Z, which is this term for us, right? But we want to get it a little closer, right? So we know it's between this value here and this value of 0.3794, which equates to 7, or a Z of 0.35, right? So what we're going to do now is we are going to have to interpolate for those values. So we have two values of Z, and we have two values of ERF of Z, and so we can linearly interpolate. So what that means is we're going to basically assume that we can, if we plot those, we can connect them with a straight line, and then we can use the slope and to determine what a point in the middle where the ERF of z would be equal to 0.4201. And so that's what we're going to do with this next step. All right, so now that we've looked at table 6.1, we've got our values. So let me just reproduce them here so it's a little easier to follow. So it gives us z and ERF of z. For our point, it was in the middle of 2 points, but our value that we calculated was 0.4210 for the ERF of everything that's inside of it. And we want to know what the z term is. And so that was between a slightly larger value of 0.4284 for the ERF of z, and then above 3794, the next value down. And so that was 0.35 and 0.40, right? So we're trying to see what that value would be for this. So again, we're going to linearly interpolate this. And so the way we can do this is with the formula for linear interpolation. This is not in your book. You can look this up online, or I've got it here too. But the idea is that you have a given x and y. So that's the way you're going to see it online. So y minus y naught is equal to x minus x naught is equal to y1 minus y naught, or 0, x1 minus x naught, or 0. So this is linear interpolation. So effectively, we have z and ERF of z. So this is effectively, this is going to be kind of like our x, and this is going to be like our y, right? So we want to know what the y value, or sorry, we want to know what this z value is. And for us, that's going to be the x, right? So the x here. And then, so this is effectively x naught, x1, and then this is x, and then this is y naught, y1, and y. So we can plug in all of the values. So kind of using this, we can plug in all of the values, and we would get something like this. It might look slightly different, but it will still work. As long as you keep track of everything, what is x and what is y. And so solving for the z term, we find that that is 0.392 once we plug all of that in. And so this is important because we know what the z value is over here, right? This is now 0.392, if we know what it is. And we can do a quick sanity check on this, right? So our value here was really close to this value. So you would expect that the x value would be closer to this value than this. And sure enough, it's 0.39, close to 0.4. So that matches up pretty well. So the importance of this is that this is the inside of the error function, right? So going back to the previous the previous work in the separate section, we saw that inside the ERF of x over 2 square root of dt was equal to 0.421. And so by solving for z, we're solving for this. This is z. So we can say x over 2 square root of dt is equal to this 0.392, right? And so from here, we can plug in what we know and solve for what we don't, right? We need to know what the time is, and we're given the diffusion coefficient, and we're given the position, right? So we know from the previous that the position is 0.5 millimeters, and then our diffusivity is 1.6 times 10 to the minus 11 meters squared per second, and then we want to know time, right? That's what this is equal to. I would probably go ahead before I plugged in the numbers and rearrange this expression, right? So if we do that, we might need some more space, right? So if we want to solve for that, we can move this up. So just moving this out of the way, moving this to the other side. And then if we want to find out what t is, we got to take the square of both sides. And so that would be dt equals x over this squared. And then if we want to get time, that's going to be all of this divided by d. All right, so it's usually better to do this before you start plugging in numbers, in my opinion. So let's go ahead now and plug in the values, right? So our position was 0.5 millimeters. However, if you remember from up here, this was in meters. So it's better to go ahead and convert those units from millimeters. And so in terms of conversion here, we have to have the conversion for 1 meter, and then that should be 1,000 millimeters, right? And so then, so you can convert this first or do it in here. Then that's going to be divided by 2 times 0.392. This is all squared, and then the diffusivity is equal to 1.6 times 10 to the minus 11, and then this is meters squared per second. The meters squared will cancel out, and you'll be left with seconds. And so when you calculate the time here, plug in all this in, we get a approximately 25,400, and this would be in seconds. This is a pretty high number, so it's more helpful to look at this in terms of hours. So if we convert, that's about 7.1 hours. All right, so this is the term that we're looking for. This is basically the answer to this question. And if we go back and look at what we were trying to solve, we were basically asked to how long does it take to achieve that carbon content of 0.8 weight percent at 0.5 millimeter from the surface, right? So our answer is it takes about 7 hours to get that 0.8 weight percent of carbon at 0.5 millimeter from the surface. This is basically telling you about the case hardening of that carbon alloy. So that's our answer to this expression of the semi-infinite carbonization question.